So today I want to discuss the just infinite property. Especially for lattices. And I want to make this talk independent of what I said last week. So let me start by recalling the definition. So a group definition. A group G is just infinite if it's infinite and all normal subgroups are of finite index. All proper quotients are finite. Okay, example Z or any infinite simple group. And you also need to know when we call the hereditarily just infinite, which is abbreviated by HJI. So if every finite index subgroup is just infinite. Okay, so that will be my notation for finite index subgroups. It's very convenient, but if you might miss the point. Okay, and so examples will be provided by the main result I want to discuss. But let me perhaps first give non-examples. So if you take S infinite simple, then G, the Reed product of S with a group of order 2, this is just infinite, but not hereditarily just infinite. Okay, it has an index 2 subgroup, which is the square of S times S. So this has infinite quotients. Right, so this is, and the cyclic group of all the two swaps. Right? And this is, but this is not a residually finite group. So if you want a residually finite example, then there is a canonical, or there is a most famous one. So the Grigorche group. The group is just infinite, but not hereditarily just. Okay. And the just infinite property for the Grigorche group is proved in a completely different way than my discussion today, which will actually be a proof that always yields the stronger, the hereditary property. Okay. So today I want to emphasize theorems and not history, but nevertheless I want to make one or two historical comments. So there is an important theorem in history due to Brenner in 1960 and Mennike in 65, which concerns the group PSLNZ with n at least 3. Then, so what they prove is that any normal subgroup of G, non-trivial, contains a congruent subgroup. The kernel the congruence quotient modulo some integer. And this is a finite ring, so this is a finite group. So these congruence kernels have finite index. Okay.
Any normal or finite index?
Any normal. So in particular, G is just infinite. Okay, so that follows from this, but much more. Not only so. This is kind of a classification of all the quotients of your group. Right? And so this theorem, it really exploits the very peculiar structure of this group, and there is a lot of arithmetic in it. And since then, you know, the analysis of quotients of arithmetic groups kind of split into two different directions. First, understand the infinite quotients, and this is what I will discuss today. And then try to classify the finite quotients, and this is the so-called congruence subgroup problem. And in a sense, for the infinite quotients, a lot of progress was made. New techniques were developed, especially by Margulis. So Margulis in '79 proved that irreducible lattices in ZLS semi-simple groups of range at least two are hereditary infinite. Okay, so this is kind of a vast generalization of this consequence of the planar Menique theorem. But the other part about the congruence subgroup problem, so this is a part where we are still limited in the techniques, as we know. And this is also reflected in my discussions about lattices in products of two trees. So understanding their infinite quotients will be possible thanks to the main results of today, but understanding their finite quotient, this remains more problematic. Oops, this does not erase. Copies. And then, after Margulis, Urgel and Moses obtained a statement for lattices in products of trees. So let gamma in out T1 plus out T2 a co-compact lattice where T1, Ti is a locally finite leafless tree. Leafless means no vertex of degree 1, and at least 3 ends. I don't want a line. So if what they prove is that if the closure of the projection of gamma on each of the two individual automorphism group is doubly transitive on the set of ends of that tree, or I equal 1 and 2, then gamma is H. So that was the tool that allowed them to, I mean, it's a theorem that has some overlap with the Margulis theorem, because some of the groups of this kind are rank 1 algebraic groups over local fields. But then what they also showed is that this theorem also applies to examples where these projections are not algebraic groups. And these are some of the lattices that we'll come back to at later stage. Okay. And then finally, the main theorem for today is, so, main theorem for today. And this version is due to Uri Bader in the User Shalom in 2006. So let gamma in G a product of two locally compact groups, a co-compact lattice. Co-compact lattice. Now we have to make assumption. The zeroth assumption is that G1, G2 are not both discrete. And then we make the assumption that they are compactly generated. Then we need an assumption that kind of says that G1 and G2 do not have too many quotients. We want to establish that gamma does not have too many quotients. So this will come from a property of the ambient group. And the assumption is that G1, G2 are just non-compact. Okay, which, so that the definition of this, you can guess it, right? i.e. non-compact with every proper quotient. Third assumption, there is no normal subgroup of Gi isomorphic to Rn. And the fourth assumption is the usual one, the dense projections. Then gamma is just infinite.
Excuse me?
Yes.
Could you provide us an example of a just non-compact group?
Yeah. So again, so if G is discrete, the assumption that G is just non-compact is exactly the same condition as being just infinite. Okay. So this covers the class of just non-compact locally compact groups. It includes all the discrete just infinite groups. Okay. But we have more. For example, take a simple locally compact group. This, if it's not compact, then necessarily it is just non-compact. Okay. Okay, so I want to discuss all these assumptions, of course, and their necessity, but before doing this, so I promised you a theorem whose conclusion was HJI and not JI. but a corollary. So if you slightly strengthen the assumption, so if in addition G1 and G2 are not only just non-compact, but hereditarily just non-compact, meaning that finite index open subgroups are. So if in addition all open H of finite index in GI is just non-compact, then gamma is HJ. Okay? And the proof of this is it's really a consequence. So you want to show, so you know that gamma is just infinite by the theorem. You want to show that a finite index subgroup of gamma is just infinite. So proof, take lambda finite index in gamma. Okay. What do you want to do? You want to, so this is still a lattice in the product G1 cross G2 because it is a finite index subgroup of a lattice, right? But now what may fail is the density of the projection. But just replace GI by the closure. So replace set HI to be the projection, the ith projection of lambda closure. Okay? So this one is a finite index. So this index is a bound, is an upper bound for the index of HI in GI. Right?
You really want open or just find index? At the,
open.
at
Open
the
is
beginning.
enough because this is a
I
closed.
know that open is enough,
Yeah.
but it's stronger than just
All open subgroups.
if you just set finite index. It's
Your condition is stronger than mine. There are a priori more finite index subgroups than open finite index subgroups.
Yeah, but you have more open and finite index.
Yeah, open and finite index.
I forgot.
Yeah, you can miss the point. Sorry.
I missed it.
Yeah, that's the danger.
Yeah.
Sorry. Okay, so that's the end, right? Because by our extra assumption, HI again are just non-compact, and all other hypotheses are inherited by HI. Okay, so that's really. Okay, so now I want to. So my main goal is to discuss the proof, but still before doing so, because the proof will have to use all of these hypotheses at some point. So no, but yeah. Well, what I want to convince you now is that the proof will have to use each of these assumptions at some point. So I want to show you why these are indeed necessary conditions. So the hypothesis are necessary. So let's start with the easiest. Okay. So if G1 and G2 are both discrete, then so a lattice in a discrete group is just a finite index subgroup. So G is a finite index. Okay, but then you have a finite index subgroup of a product group, and then it's virtually a product. Actually, so in that case, both projections will give you proper quotients. Both projections. proper quotient. Okay, so then it cannot be just infinite. So why do we need that G1 and G2 are compactly generated? So this requires, it took me a bit more time to come, because you see, so another point I want to make is that, so this is a very striking result that I find. So its scope looks, it's amazing that you can derive such a strong conclusion from very abstract conditions of that kind. But on the other hand, we don't have so many examples, explicit examples, where this theorem applies and none of the previous ones applies. Of course, in the setup of where Margulies' theorem applies, we have many examples, the arithmetic groups. Then we have a couple of other examples coming from lattices acting on products of trees, but then the Burger-Moses theorem applies. And then we run out of sources of examples. I mean, here there is this is almost true. Okay, so that's, when I see this theorem, I really wonder what are these locally compact groups, the product of two locally compact groups, having a lattice satisfying this. And the question is, there are not so many examples. I don't know many examples, and examples are not easy to construct. Nevertheless, so if you allow non-compactly generated groups, then here is a way to construct an example. So G1 will be just Z. It's just infinite. So hence just non-compact. And G2 will be P gamma L2 over Fp bar, where P is a prime. So this is the algebraic closure of the field of order P. And P gamma L is just PGL2 extended by the Galois group. Okay? So this Galois group, this is a compact group, isomorphic to Z hat. Okay? And this is a countable group, so I endow it with a discrete topology.
What's Z hat?
So Z hat is the profinite completion
Oh, okay.
of Z. So this is the product over all primes. Yes. I should write the q-adic integer. Okay. And so this is an algebraically closed field. So PGL2 and PSL2 are the same group. So this is simple as an abstract group. So what you can deduce is that G2 is indeed, it's non-discrete because this one is non-discrete, and it's just non-compact. The only proper quotients are from quotients. I mean, we kill the simple normal subgroup, which is the standard. So you see that G2 is just non-compact. And now, what is the lattice? Gamma will simply be PGL2 FP bar extended by Z. Okay, and I embed this in G1 plus G2 in the obvious way, right? It's a dense subgroup of this, and I just simply map to G1 via the obvious quotient.
The action is the restriction of the action of the group already.
Yeah. So this acts as a Frobenius. Yeah. So the action is by Frobenius. The Frobenius. Okay.
So if I'm betting it's just into G2.
It injects in G2,
Yeah.
but it maps. It has a natural map to G12,
Yeah.
and it's a surjective map, so if you can check that all the assumptions are satisfied, except one. So G2 is not compactly generated. So all the compactly generated subgroups of G2, they will be generated by finitely many cosets of this group. So it will be a compact group. So because this one is a locally finite group. So every compactly generated subgroup of G2 is compact. And so the group is not just infinite because it has Z. Okay. So I should leave the statement of the theorem there. So, how do you build an example for 2? You do the following. So, take gamma to G1, G2, satisfying all the assumptions. So that's a just infinite group. The theorem applies. And now the counter example that will fail to satisfy 2 is just gamma cross gamma that we view as a lattice in G1 cross G1 cross G2 cross G2. Okay? And now you group the terms this way. Okay, the projection to both is dense, but this is not just infinite, and these two groups are not just non-compact. Is that okay? G1 cross G1 and G2 cross G2. So for 3, okay, so the example is as follows. Take gamma to be Z squared extended by C2, and C2 acts just like plus minus 1. And G1 will be
Wait,
and G wait, yes.
C2x by interchanging the
No,
by just
plus minus 1. So
okay, just multiplication by
yeah,
minus 1.
multiplication by minus 1. And G1, G2 are the isometric group of the real line. Okay, and then I view Z as, for example, as the additive group of this ring. And I embed it in G1 and G2 via the two real embeddings of this ring. Right? So in that way, it becomes an irreducible lattice. So the two real embeddings. So that will be an irreducible lattice. So R is a beautiful example of a just non-compact group. So its only proper quotients are the circle. So we really again verify all the conclusions except all the hypotheses except the third one. And you see that this one is not just infinite, right? You can kill a cyclic is not Okay, and then for the fourth, then the easiest for me is to refer to my previous talk. So gamma 2 from previous talk. And in that case, G1 was G2 was the automorphism group of the 4 valent tree. I mentioned that this has the infinity as a quotient. It has an infinite dihedral quotient. So these groups are just non-compact. And again, so yeah, that will be an example. Okay. Right. So my next goal is to answer more properly the question about just non-compact groups. So yeah, from the point of view of this theorem, it's the right notion, just non-compact groups. It's exactly the non-discrete analog of the just infinite property. But it turns out that there are not so many just non-compact groups already. So that's something that we observed with Nicolas Migaud. So that's just a theorem about abstract locally compact groups. So let G be a compactly generated just non-compact group. Then one of the following assertions. Either G is discrete, or G is Rn by compact. For example, Rn semidirect On, that's a nice just non-compact group. And the third possibility is that G is an extension of a direct product of d copies of S by a compact group, where S is compactly generated, topologically simple, non-compact, and non-discrete. Okay. So in other words, to build just non-compact groups, there are only, if you stay away from the discrete case, there are only two ways: extensions of Rn or extensions of direct powers of simple groups. Okay, and
So the right case enter into free. But it can be one copy and so that's the most important.
yeah. So
Almost everything is in free.
yeah. So in this theorem, we exclude this by assumption 3. Okay, so this will never occur, and we assume that either G1 or G2 is non-discrete. So at least one of the two factors will be of this kind. And I will soon prove a lemma saying that actually both factors are of this kind. But before doing this, let me say, okay, just also for later references. So in addition, in case 3, every closed normal subgroup of G, which is non-trivial, it contains this. So in particular, it's non-discrete. Hence, it's non-discrete. I will use this in a minute. And also there is another comment is that any morphism, any continuous to a compact Lie group has finite limits. Okay, so these are things that you can derive from this description in case 3. I will not dwell on this. So, but basically, so either the group, the simple group here, is connected, in which case it will be a simple Lie group. But then the point is that the compact piece here must be finite. This is just because the auto-automorphism group of a simple Lie group is finite. So basically the only possible action for this modulo of finite bit is to permute. So yeah. And you cannot have embed a simple, non-compact simple Lie group in a compact one.
So I have a question about this. So your definition of just non-compact, you take every abstract quotient or
No,
closed?
yeah, every proper Hausdorff.
And
Yeah.
on topologically simple, you take care only of closed ones.
Yeah, every proper Hausdorff quotient is trivial. Is one of the two trivial ones. Yeah. Okay, so these are two remarks that we'll use later.
Where did this come from? This is very surprising. Isn't it?
This theorem?
Yes.
Yeah, I mean,
Listen, what about simple Lie groups, for instance?
yeah, they're here.
So they're here where you have
S
only one
is
factor.
just any compactly generated topologically simple. So simple Lie groups will fall into case 3. And also, I should say that so there is a finite in so the group, it must permute transitively all these factors. Otherwise, so if I have two different orbits, then I would have normal subgroups that yield non-compact quotient. Okay. So there is a permutation action of G on a finite set, and the kernel of this action, which is a finite index open subgroup of G, it will have non-compact quotients unless there is only one factor. So this means that in the hereditarily just non-compact case, I have only one factor. So if G is hereditarily just non-compact, only one simple factor S.
How does the proof work? Do you prove that if G is non-discrete and not owned by compact, then it must be like?
Yeah, you assume that G is non-discrete. You don't exclude 2 a priori. You have to discuss the identity component of G, which is a closed normal subgroup. So it's either trivial, which is a group is totally disconnected, and then you can proceed from there, or the identity component is not trivial, but then it's co-compact, and then you can use the structure theory of connected locally compact groups. So, yeah. Okay, so now let me let me use this to establish a first lemma which plays a role in the proof of the main theorem. So, yeah, I want to keep this and I want to use this. I don't know what to do. Anyway, this, yeah. That's the main result. So. So here is a lemma. So let gamma in G1, G2 be a lattice with dense projections and with satisfying all the assumptions. Okay. Then I claim that both di are non-discrete that's the first thing. And two, the projection from gamma to gi is injective. Okay. So this will play the injectivity of the projection. This will play a crucial role because so what we will have to do is to consider a normal subgroup of gamma and use G1 and G2, and we'll project the normal subgroup of gamma to both factors, and we need to ensure that both of these projections are non-trivial. So this failed in one of our previous examples. Okay, so proof. Okay, so we know that, so we assume, we know that they are not both discrete, so we assume G1 is not discrete. And we show that the projection to G2 is injective. And then this will imply both. Okay, so let lambda be the kernel. So gamma intersected with G1 plus the Okay, so that's the kernel of the projection to G2. Okay, so this is normal in gamma. So I project this onto the first factor. Okay? But now, by the nature, by the definition of lambda, I see that this projection is actually discrete. But so a discrete subgroup is closed, so its normalizer is closed, so it must be normalized by the whole group G1. Okay. So this is, I'm just using the fact that discrete subgroups have a closed normalizer. But G1 was not discrete, so in my previous theorem, the only possibility is that G1 is of type 3. And in type 3 groups, the non-trivial normal subgroups are always non-discrete. So G1 is of type 3. So the only discrete normal subgroup is the identity. Oops. Okay. So this shows that the projection is injective. And now, if it remains to show that G2 is non-discrete. So if we prove this, then we can do the same argument with G1 and G2 interchange. But now if G2 were discrete, then G1 cross 1 is open. But then, so if you intersect a lattice with an open subgroup, this is always a lattice in the open subgroup, just because the hard measure is the restriction of the hard measure on the n group. I mean, that's a general fact which is not too difficult. So then, gamma intersected with this is a lattice. So it cannot, and because G1 is not compact, that cannot be the trivial. Okay, so that's the proof of the lemma. Okay. So now we come to the discussion of the proof of the Waller-Charles theorem. So the strategy is due to Margulis. So it is to show, to take a non-trivial normal subgroup and to show two theorems. Gamma mod n has property T, and gamma mod n is immutable. And in this framework, so this was proved by Shalom himself in 2000, and this is the contribution of Adel Shalom in 2006. And these two parts are, two completely different proofs, each of independent interest. And yeah, I will focus on the property T half for several reasons. One of the reasons is that the amenability half, well, it's more analytic in flavor, and also it's valid in a greater level of generality. So you don't need all these assumptions, actually. So I won't have the time to go into this. And I want to discuss this, and this has slightly more geometric flavor. And this is what I want to explain. Okay, so we focus on the property T. Okay, so to do this, I need a definition. So a group, which is due to Shalom, a group G, a group action, sorry. On the metric space, X is called uniform. Sorry, I need a name for the group. An action of a topological group G on a metric space X is uniform if there exists a subset Q in G compact, and there exists epsilon such that any point of the metric space is displaced by some element of Q by at least epsilon. Okay. So this is reminiscent of almost invariant vectors, right? So what you should have, perhaps what comes to mind first is if X is a unit sphere in a Hilbert space, with the induced metric. So what does it mean that the action on that sphere is uniform? It just means that there is no almost invariant vector. G on X is uniform. Finally, there is no almost invariant vector.
Just a stupid question. Is uniform a good terminology?
It's Shalom's terminology. I don't like it
It's a bad
very much.
terminology. It should be separating or something like that.
Yeah. Yeah, it suggests co-compactness, which is of course not at all what this is about. Okay, so but you have many other situations where for the proof we mostly look at affine isometric actions on Hilbert spaces, but even before mentioning those, so here is an exercise. So if X is a proper K0 space, and G an isometric group acting without fixed point in the space or at infinity, then the action is uniform. But not, of course, not necessarily co-compact. So that's an exercise.
Wait,
And
what do you mean uniform in that setting? You don't have a metric on the whole space. X union its boundary doesn't have a metric?
No, I'm not looking at the action on the
just on the
compactification.
X.
I want no fixed point in X.
And no fixed point
And-
boundary.
Sorry,
Okay.
no fixed
I
point
missed it. Okay.
Uniform on X.
If I exclude fixed points both in the space and at infinity, then the action has this separation property. And now if X is a Hilbert space, and G acts by affine isometry, okay, then essentially there is an analog of this which is still correct, so no fixed point. And then I want to say no fixed point at infinity, which means no non-zero invariant vector for the linear part of the action. But this is not enough. So if I assume that there is no almost invariant vector for the linear part, okay, then again the action is uniform. Okay. So why do we introduce this? Okay, now I will describe how you get the property T half in the Shalom theorem. So this consists in putting together three results, all due to Shalom, and each of them of independent interest. So let me explain them one by one. So theorem one. Let G be a compactly generating without property P. Then there is an affine isometric action on some Hilbert space, which is uniform and whose linear part is irreducible. So this is a result where where the assumption of compact generation is essential. Otherwise, there are counterexamples, and it's also a result that we will only apply in the discrete case for the group gamma, or a quotient of the group gamma. Okay, and in the discrete case, this theorem was given another short proof by Ozawa recently in the appendix to his paper, where he gives a short proof of Gromov theorem. So, if you want a quick, concise proof of this theorem in the discrete case, which is the only one we need here, I recommend to look at Ozawa's theorem. I will not go into this proof here. Okay. The second theorem is a kind of superrigidity size theorem. Let gamma be a co-compact lattice with discrete projection, with a dense projection. C1 compact unit. And let gamma act uniformly by affine isometry on a Hilbert space. So
your actions are proper?
no, absolutely not.
Just according to.
Yeah, we just assume. So superrigidity is something that starts with a gamma action and promotes it to an action of the envelope. And so what this superrigidity statement will say that the linear part of this affine action of gamma has an extension. Okay, so this is what I'm about to write. So then the linear part I has a sub-representation I prime which extends continuously to G via a projection to one of the factors. So that's what I want to write. So there is a sub-representation and continuous representation I prime tilde from Gi to the unitary group of H such that, so it's really an extension, phi prime of gamma is equal phi prime tilde of the projection gamma to phi for all gamma and gamma. And I is 1 or 2. Okay, it's just there exists I such that in this extension. Okay, so that's kind of really the one of the core results. And yeah, if I have time, I will come back to the proof of that. And then there is a third theorem. So you see, one case where this superiority does not yield too much information is when the linear part of this affine action of gamma is trivial, which means that gamma acts by translation. Okay, translation action can be uniform, of course, even in the finite dimensional case. But in that case, the superrigidity statement here is not very useful. But then, fortunately, there is another theorem saying that for the trivial representation, everything goes well too. So let gamma in U1 cross U2 as in theorem 2. Then every homomorphism from gamma the additive group of C extends to continuous homomorphism. Okay. So now, yeah, what I want to do is to, if you accept these three results, I want to derive the proof of the theorem, of the main theorem. So now what I want to explain is that theorem 1, 2, 3 implies the property half. Okay. So what do we have to show? We have to take n, the normal subgroup of gamma, the non-trivial one. Okay. And we need to show that gamma with n has t. Okay. So the proof is by contradiction. Assume it does not. Okay. So if it does not, then we want to apply theorem 1. What do we have to show? We have to show that gamma mod n is a compactly generated locally compact, but it's a co-compact lattice in a compactly generated group, so it will be compactly generated. So we apply theorem 1 and gamma, hence gamma mod n is finitely generated. See. Oops, I think we're. Yeah. Sorry. But my apologies won't be transmitted.
We can hear you.
You can.
We have backups.
Okay. So gamma mod n is finitely generated because gamma is co-compact. Okay, so that's one of the places where we use the co-compact assumptions. So we get a uniform affine action of gamma mod n, of gamma on H, a Hilbert space, trivial on n. Okay. So that's what and whose linear part is irreducible. So just apply theorem 1. So I can erase. Okay, now we apply theorem 2. Okay, so theorem 2 says that a sub-representation of pi, the linear part is pi, extends continuously, but pi is irreducible. Okay, so pi, theorem 2, implies that pi extends to G1 or G2. I mean to G via the factor map to G1 or G2. Okay. But now, so i.e., so there exists pi tilde, let's say G1, such that it's an extension, right? Pi gamma tilde the projection. But now we want to use the fact that our affine action was trivial on n, so the linear part of the action is also trivial on n. So what we get, so this is trivial. Okay. But this is a continuous representation, so it's also trivial on the closure. Right? But we checked before that this projection is injective, so we indeed get a non-trivial normal subgroup for Gi or G1, which acts trivially. But what does this mean? We have assumed that every non-trivial normal subgroup is co-compact. So pi tilde of G1, it goes to this quotient, which is compact. So this is compact. So we are looking at an irreducible representation of a compact group. So pi was irreducible. So the extension a fortiori irreducible, but irreducible of representation, a unitary representation of compact groups are finite dimensional. Okay. So in particular, this extension so pi tilde is actually a homomorphism from G1 to SUN. Okay. That's trivial. That is not injective. But I remarked before, so by previous remark, we know that G1 must be in the third possibility of my result on just non-compact groups. So the image to SU1 was necessarily a finite group. Okay, but this means that phi gamma is finite. Okay, so the affine action of gamma is on a finite dimensional Hilbert space, and it has finite linear part. So if I replace gamma by a finite index subgroup, what I'm looking at is just a character of gamma, a homomorphism to the additive group of a finite dimensional real vector space. Okay, and then I just use theorem 3 now. So a finite index subgroup of gamma has a non-trivial homomorphism. But finite index subgroup lambda of gamma that is non-trivial. Okay, and then I apply theorem 3 to lambda, and as before, I can replace G1 and G2 by the closure of the projections. And I don't violate the fact. So if I do this replacement, I still get two locally compact groups that need not be just non-compact anymore, but still they do not admit any character. Okay. So basically, that's the end of it. So a contradiction. Okay. Yeah, so I was planning to say a bit more on the proof of the superrigidity theorem, which is very striking. I mean, all three results are of, as I said, of independent interest. But in a sense, so you haven't really seen where the assumption that the ambient group is a product group plays a role. And that's really in the proof of theorem 2. So there is a key fact. I will finish with this. Because this is really something that has a lot of geometric content. So the key to theorem 2 is the following result. Let G be a product group, act uniformly by affine isometry on a Hilbert space. Then G1. So then the linear part has a non-zero fixed vector under G1 or G2. So this is just a result on a product group action by affine isometries on a Hilbert space. You assume that this action satisfies the separation property. And the conclusion is that either G1 or G2 has a fixed point at infinity. Okay, so compare, let G a product group act uniformly on a proper Cat0 space, then G1 or G2 has a fixed point at infinity. You see, that's the analog of this statement in the realm of proper Cat0 space, that this statement and this statement is it's actually due to mono. I think in that form. It follows from a splitting theorem. So for this theorem, so how do you establish this? You first look at the possibility. So G acts on the Cat0 space X. If G, the whole group G has a fixed point at infinity, you're done. And if not, then you know that you can pass to a subspace, a minimal invariant subspace, by the properness of X. And now Mono proved that if you have a product group acting minimally on a proper Cat0 space, then actually it's a product. The space has a product structure, and the group action is a product action. But in a product action, you know, at least one of the two factors is fixed. And yeah, maybe it's a good place.
Wait, what are the assumptions on G1 and G2?
No assumption. It's just a product group. You just for either of these results is just. And so the fact that this is very geometric in flavor and has analogs in the Cat0 setting, it was actually exploited by Nicolas Monod to prove a superrigidity with Cat0 targets, which is kind of in the same spirit as Shalom's theorem 2 that I presented. But it's not a strict generalization of Shalom's theorem, because if you really want splitting theorems for Cat0 in the Cat0 setup, I'm not sure you can do it with the uniformity assumption. Yeah. So Mono used a much stronger condition to, and so his superrigidity theorem will not apply to uniform actions of lattices in product on Hilbert spaces, whereas Shalom's theorem does apply. And why is this useful for theorem 2? Maybe let me conclude with this. Okay, so now back to theorem 2. So we start with gamma acting on H uniformly. Okay. So what you do, you induce the action to G1 plus G2 on another Hilbert space. I mean, there is something fishy here, because induction is very standard for linear unitary representations, but if you want to induce an affine action, there are technical difficulties, and that's the other place where the co-compactness of the lattice is used. I will not go into this. But the point is that you can induce, and another result of Shalom is that once you induce a uniform action, you get something which is still uniform. Okay. But now the key proposition says that the linear part of this and the linear part of the induced affine action is the induced. So by the key proposition the linear part of the induced affine action, which is nothing but the linear induced action, has non-zero invariant vectors under G1 or G2. But now it's an exercise about induced representation. If you have this situation of a lattice in a product, I mean, you can even prove this exercise for representation of finite groups. You induce a representation from a subgroup to the ambient group, and you assume that the ambient group is a product, and that G1 has a non-zero fixed vector induced representation. Well, it tells you something about the initial representation gamma. This one only depends on gamma via the projection to G2. So there's, you finish with, you know, a lemma on induced representations. But it's a lemma that's, yeah, you can understand even, you know, at a very elementary level. Okay, so I think I'll stop here for today.
I'm confused by what you said in Monod's theorem. If you take G, the free group acting on the scalar graph,
Yeah.
isn't that a uniform action on a proper Cantor space without fixed, doesn't
Yeah.
have fixed point?
But that's not a product group.
And what if you take F2 cross F2 acting on the product of trees?
Yeah.
Then it doesn't have fixed point.
Yeah, it does. Each individual.
Yeah, think of it.
The boundary's two counter sets, this is
Oh,
the joint of
yeah,
two
yeah,
counter
yeah,
sets,
right.
it fixes the other counter set.
Oh, I see, yeah. Okay.
Yeah. So the boundary, so it's a product of two trees.
Oh, yeah,
And
and
the second free group,
Yeah.
so the one that acts on the horizontal tree,
yeah,
right?
fixes the.
It translates the vertical tree, but it acts trivially on the boundary at infinity of the vertical tree. Yeah, so it's so theorem 3 was also generalized by Burgel and Monod for example, extensions of quasimorphism. So all those interesting. So there is the fact that characters extend continuously from the lattice to the ambient group. This has a version due to Burgel and Monod. Quasimorphisms. And as I said, theorem 1 is the first step in Ozawa's proof. Theorem 2 is related to nonlinear superrigidity. So it's a lot of material, but yeah. Very interesting. So next week I will start again a new subject. So I will speak about subgroup separability and residual finiteness. So that I want to start the discussion of how do you construct lattices that are not residually finite. Okay, so I will start from scratch, and it will be probably a lot more pedestrian in some sense.
So if we consider what you told us today, like for Bourdieu-Moses group, it was like also proof like for each theorem you have analog or?
Yes.
Okay.
Yeah, for the Burgel-Moses case, it's also you need to combine two theorems, one a property T half and a amenability half. And they did it differently, both halves. They did it in a bit closer in spirit to Margulis. Yeah. And I should say that, so probably this is not visible in the way I stated the results, but really the Badel-Shalom theorem is really a generalization of the Burgel-Moses theorem. Burgel-Moses, you didn't see just non-compact groups, but you saw a double transitivity condition of the projection. Okay. But Burgel and Moses proved a theorem saying that, a structure theorem for groups acting on trees, saying that if a group acts on a tree, if you take a closed subgroup of the automorphism group of a tree, and the action is doubly transitive at infinity, then the group is hereditarily just non-compact. So it's really...
So it is included as a particular case
Yeah,
now? Or
yeah,
this?
absolutely. And what's not included is, of course, Margulis' theorem in its full generality, because Margulis' theorem also applies to lattices in high-rank simple Lie groups. It's only one factor. So that's a kind of something that hasn't been generalized to a more abstract setting. I mean, it's not quite true, but the problem is that we don't know how to make sense of a high-rank assumption or a simple locally complex group. And, so it's not even clear what the statement would be. But in the other direction, we do have generalization. Maybe this is something I can mention. So in Lie groups, of course, you have the simple Lie groups of rank at least 2, where Margulis theorem says lattices are hereditarily just infinite. But then you also have the simple Lie groups of rank 1. And their lattices are well understood. The uniform lattices are hyperbolic groups, in the sense that the non-uniform lattices are relatively hyperbolic. And none of those are just infinite, right? We know that hyperbolic groups, like Gromov-Delezan, they are SQ universal if they are non-elementary, and similarly for relatively hyperbolic groups, as was shown by Unara and right, Ashot. Right? And now, so this result has an analog. So maybe let me write this analog. So that's kind of the rank 1. So we don't know what a rank 1 locally compact group is, but we know what a rank 1, a hyperbolic locally compact group is. So the result is as follows. So let G be a hyperbolic locally compact group. I just mean a locally compact group which is compactly generative and is hyperbolic with respect to a compact generating set. Then any lattice is just universal. I should say non-elementary.
Because they are hyperbolic? Gamma is
No,
not hyperbolic.
so if gamma is co-compact,
Yes.
then gamma is hyperbolic. And so it's Delezan Gromov.
I think it's a result of a chance. There is no problem.
What?
It's a result of a chance.
Okay. Thank you. And now if gamma is non-uniform, then we cannot conclude that gamma is relatively hyperbolic. But now we have the right concept. We can always conclude that gamma is acylindrically hyperbolic. Okay. And this in turn implies the universal by Germanie, Mirabel aussi. Okay, so I like to mention this fact because it's kind of the same in my opinion that we understand well infinite quotients in the rank 1 case, but we don't understand finite quotients. We don't know whether a hyperbolic group can be readily finite. So it's kind of, yeah.
Cannot be. You mean cannot be? You don't understand it cannot be.
Yeah.
Okay.
We don't understand whether, whether a hyperbolic can be non-readily finite.
I think I missed. So how you see that asymmetrical and non-uniform?
Yeah, because it will be a discrete. So this will be a discrete group acting. So its action by left multiplication on G is proper, and G itself is a locally compact hyperbolic metric space. So yeah, so you get, and the fact that it's a lattice, it's easy to deduce that you have north or you have elements doing north.
It's
Yeah.
not necessarily relatively hyperbolic?
No.
Oh, when is it not?
That's a good question.
Oh, okay. I thought they were, that's what I'm asking. I would say they were.
Yeah, so if gamma in G non-uniform lattice is relatively hyperbolic and G is hyperbolic, then G is a rank 1 simple leap, or G is Qi to a tree, and with doubly transitive action. So this.
Who did that?
So this is part of the paper with Cornelius. Okay, so if you take then it's an yeah. You can construct example even acting on trees. You just take a suitable tree such that the automorphism group is not doubly transitive at infinity. For example, it's enough to find a tree which is not semi-regular. And the automorphism and find a non-uniform lattice there. It cannot be. But yeah.